So thanks everyone. I will talk today about the sPHENIX experience with ACTS so far. We've been using and working on implementing the software into our software stack for about 3 months now, so we're still relatively new. So just to give a quick overview on sPHENIX, since it may not be as well known in the more high energy physics community, sPHENIX is a heavy ion experiment that is located at the Relativistic Heavy Ion Collider, or RHIC, at Brookhaven National Lab. So RHIC will deliver gold-gold collisions up to 200 kilohertz into our nominal interaction region. So this will give us, on average, 3 to 8 heavy ion pile-up events per bunch crossing. So we are going to be experiencing sort of occupancies that are expected at the high luminosity LHC just in heavy ion events in the next couple of years, as sPHENIX will start collecting physics data in 2023. So our data processing is planned for a fixed latency, finite size computing center at Brookhaven, and thus we require a high-speed, efficient, and precise tracking software in an environment where of order hundreds of thousands of hits are expected in our detector. And we also need to reduce our tracking time to less than 5 seconds per event in these conditions. So ACTS is a perfect potential solution for us. So just to give a quick outline of the sPHENIX detector, we have some silicon tracking detectors like most people, or like most experiments do, at the very center of our detector. So we have a MAPS-based vertex detector, and then what's called the intermediate tracker, which is a silicon tracker. Outside of that is the TPC, which is this yellow cage here, which there will be some more discussions about this later. And then we have our electromagnetic calorimeter, and then 2 hadronic calorimeters for improving the jet energy resolution in heavy ion collisions. So sPHENIX is nominally a central barrel detector. We do not have any forward instrumentation at this time. So just to talk about our implementation with ACTS. So just to mention that the GitHub migration of ACTS has been extremely useful for us, and I would assume other external to CERN experiments also. So we now have a fork of ACTS that we include in our sPHENIX build, and we can just very quickly pull the new changes that are in the ACTS master repository into our fork. And this is a 5-minute process now, which is greatly improved from the previous GitLab experience. So just wanted to mention that we really appreciate that, and it's been extremely helpful for us. So we're using the T-geometry plugin within ACTS to construct our silicon surfaces, which are the 3D rendering are shown here. So Andy was very helpful in getting us set up with this. The TPC remains a challenge at the moment, as ACTS does not support these kinds of geometries currently. So at the moment, what we do is we modify our T-geometry manager to build boxes, which then the TGeo ACTS plugin picks up and builds surfaces out of. So this is a 3D rendering of our ACTS surface geometry. So if you look carefully, there's some green and purple surfaces in the very center of this. Those are the silicon tracking detectors, and then this very large set of black boxes are the boxes that we just nominally build within the TGeo manager and have ACTS pick up. So this is fine for us for the moment, as we are really just working on getting things set up and working, and we need to continue making progress, but of course this won't be viable long term, especially with some considerations for the TPC that need to be taken into account, like space charge distortions. So in principle, all of these boxes will have to be moved because of space charge distortions, but we can come back to that later. So just to give a quick update on our current status, we can run the ACTS Common Track Fitter and combinatorial Common Track Finder. So at the moment, we have GenFit running our track propagation, and then we feed the results into the ACTS Common Track Fitter. So we're just using that at the moment, since we know that the GenFit track propagator works, and the fitter is what takes more time anyway. So this is just to show some timing tests that we did. We have run the Kalman filter time test for a single 4 GeV pion track. Again, we're trying to get a sense for how slow ACTS is, given that we have these many thousands of surfaces in the TPC that are being built. So this red histogram here is the case where we have 11 surfaces in Z per TPC half sector, and this basically corresponds to 70,000 total surfaces in the TPC. And then the black histogram is cutting this by an order of magnitude. So having 7,000 TPC surfaces, and of course, as one might expect, the track time drops pretty significantly when we have only one Z surface per TPC half sector, but it scales about linearly. This is just to give us a good sense of what track times we should expect and how we might tune this TPC surface building that we're doing at the moment to improve the track time. So our track fit doesn't seem to be completely correct due to what I believe is the covariance matrix rotation. So I'll talk about that now. So I mentioned the track fitting is in place, but I'm still not convinced that I'm implementing the covariance matrix rotation correctly. And the reason is that we have some very large tails that are present in the track fit results. So this is a plot that shows, for example, the reconstructed by, when I say reconstructed, I mean the result from the ACTS Kalman filter, X momentum component divided by the truth X momentum component for some simple 5 pion events, where the PT is a couple of GeV or so. So clearly there's some track fits that converge and are working, since this is sort of centered close to 1 and there's a nice peak, but there are these really long tails that I would assume is an indication that there's a number of track fits that are failing or not converging correctly. So just as an additional comment, this bottom plot here shows from the same data sample the reconstructed Z point of closest approach as returned by the ACTS Kalman fitter compared to the truth Z point of closest approach. And you can see again, there's some nominal distribution around 0, but there are these very long tails. And in addition, the Z point of closest approach is actually very poorly fit. You can see the scale of the y-axis here compared to the X momentum plot above is very different. So there are a significant number of entries in this plot that don't even show up on this scale. So there's still something that's not being implemented quite correctly on our side, I believe, or some misunderstanding that we have. So just to, this is sort of my summary slide, and to just mention some challenges that we have faced and that we are facing to start some discussion. So the TPC is an obvious one that also Bell 2 has already mentioned for their drift chambers. How will we implement it long term? Originally, we had some idea to dynamically generate surfaces on the fly based on a measurement position in the TPC volume. So the pros for this are that it could be flexible and could potentially be implemented for virtually any geometry, but for us at least, this will probably be extremely memory hungry, especially for our TPC scenario where we expect hundreds of thousands of hits per event. Another thing that we need to consider is that in our TPC, we have space charge distortions that come about from a strong induced electric field that is created from the ionized charge. And this displaces the measurements over the course of the TPC drift time by millimeters. And this is probably one of the biggest challenges that we are trying to learn how to address in sPHENIX right now. So a nominal question then is, how do we actually handle this within ACTS? And that's a question that we have not quite understood yet how to solve. One other thing that I would mention is that, again, our track fitting seems to be moving in the right direction, but the covariance matrix rotation has been a challenge for us to understand. Personally, for me, it was not obvious that the covariance matrix should be in local coordinates, since the track parameters actually take global position and momentum vectors. And so I initially assumed that everything should be global. We nominally have our track covariance matrix in global XYZ and PX, PY, PZ basis, and ACTS expects a local basis. So after many discussions with Zhao Kong and Fabian, I really appreciate their help and probably my incessant question asking. I have understood it better in the last week or so, that this local basis actually corresponds to a surface that is centered at the point of closest approach with a normal vector along the momentum vector. But that wasn't apparent to me at first. So the only documentation that we've really been following is the reconstructed truth tracks example. And I think it would be, as a suggestion, I think a realistic example, starting from a detector object and running through an entire track fitting process would be extremely useful. And I think there was already, if I heard correctly, there was already some discussion about this earlier in today's session. So I think that would be a very helpful and useful thing that would, at least for me, would have helped me get going with this step more quickly. So that's all I have for today. Thanks, everyone, and I'm happy to take any questions.
Great, thanks, Joe. Any questions? Oh, lots of questions. Moritz, go ahead.
Hi, can you hear me?
Yes.
Yep.
Yeah, excellent. So thanks, Joe, for the nice talk. I have actually a comment and a question. First one, a comment regarding the track parameterization. I think the problem is that in the past, we've not been very clear in what the different parameters do. We now have in the code base the concept of 3 parameters, which are the XYZ type global coordinates, and we have the concept of bound or local parameters. And your experience shows that we should really do a better job at distinguishing the two and making really clear what each of those entail. So thank you very much for bringing that to light. The question I had is more a technical one. You mentioned that you were including the fork within your local builds. Are you doing that with a custom installation, or do you do that just with an add subdirectory call? Just out of curiosity.
So we do it with a custom installation, I think. So our builds, they basically just link directly to our fork, and they just pull the code from the fork and then use it to build also as an external library. So because we have implemented some of our own classes within our ACTS fork, which is why we're not, for example, pulling directly from the master repository. And that's why we have sort of our own fork that we're working within and have made some changes for ourselves. And just also as a comment to your first comment, I think also part of my confusion was that I did not understand what bound and free parameters meant within ACTS. And I don't know if that's Atlas jargon or something like that. So I would definitely agree that I think it would be very helpful for people who are outside of, maybe these are common jargon words that are used in high energy physics and not nuclear physics, for example. I'm not sure.
Well, we came up with those, Joe.
Oh, okay. I didn't know, so I didn't want to assume.
They certainly need a better documentation, both in the code and now in the new read the docs area, which we created 2 weeks ago.
Yeah.
Okay, let's move on. So Shakong, you have a question.
Yeah. So for the common feature, have you managed to look at the efficiency of the fitting to see if it looks normal?
I haven't looked very carefully, but I have noticed. I think in one of my times where I was asking you many questions, I think I asked how many track fits I should expect to fail, and I think there are still many track fits that return some error message, or too many track fits that return an error message. I think it's of order 10% or something like that. So again, that's some indication that I'm clearly not doing something correctly in terms of preparing the track seed for the common fitter.
Okay. Yeah, so I think that could be the reason. If the common feeder is working normally, we should see a higher efficiency. Yeah.
Mm-hmm. Yeah, so I expect there's still something that I just am not understanding or something, but at least I was very happy to see those plots that I showed on the previous page, because it's at least an indication that I'm going in the right direction.
So can I just, from a procedural point of view, can I suggest that as we have Wednesday and Thursday relatively loosely laid out, if we can find, for instance, a spot where Fabian, Jacong, you, Joe, can discuss a little bit in a smaller circle, and we probably can then nail down the remaining items such that you can make a step further.
Sure, that would be very helpful from my perspective.
Okay, sounds good. Marcus.
Yeah, I need to unmute. Hi. And I'm still a bit puzzled about this TPC problem. I mean, what kind of TPC is does it have pads or gems, or what is it?
Yes, it has gems.
Uh-huh. I mean, it's the how many hits do you get per track?
So in a single track environment, it's about 50 to 60 hits total.
I mean, but in principle, in these gems are regular mesh, so you can put. I mean, you can just draw circles through it, right?
Draw circles through what? I'm not sure I understand what.
I mean, it's if you look at where the possible hit positions are, there must be on circles, which are following a different radius.
Sure, but the part of the problem is that the space charge distortions completely distort that. So the space charge distortions
I understand that, but
so yeah, go ahead, Marcus.
Yeah, and I mean that's the usual problem with the TPC, but you can work in projections with the space charge distortions and use cylindrical extrapolation layers where you need 50. Or maybe twice 50 or 100 or so.
And we don't even need that. I think that is our current understanding, because what Joe clearly shows, and it's not it's far from unobvious, is exactly what you should expect. The more layers you put in, the more time you spend, because all of this adds almost unnecessarily navigation intersection checks in the fit. Yeah. I believe we can get along.
You don't have to put these additional all the 50 layers into the navigation, because
exactly
TPC is a continuous volume anyway.
That's what we would like to
do. But I mean, for the hits, I mean, if you use a cylinder coordinate system and you use the local position as the hit position in the drift volume relative to the end cap, I mean, then that's okay. I mean, I agree with you. I would not put these 50 into the stepper. That I would not do. But but to avoid dynamically curating all the surfaces for the extrapolation for all the hits, I mean, you just use 50 and you work in these projections.
Yeah. So the propagator actually, we could equip it even not that you don't even need to have the surface created. We could equip it with an actor that knows the geometry or your TPC geometry and just stops at certain radii, and then you have your reference points. Then you need to locally calibrate them, of course, but at the end, I suspect we can get this almost surface free, which means no much navigation, except for I'm in the TPC volume, and this is, I think, a perfect item which we should like spin out and try to lay out how we would tackle that. It has already started, to be honest. Xiaokong, Fabian, I think, are talking about this already with Joe since some time.
And yours would have the advantage that you could do the distortions in 3D.
Exactly.
Yeah.
So since in the Kalman filter, the calibrator and the actor would come together, you would have the right space. You would stop at the right space and have the calibration by your side, and I think that would be an ideal way. But I don't want to preempt this discussion. So just,
I think let's actually pause this discussion here. It was a very good discussion, and then we'll continue it. I guess we should choose. I guess we're going to continue it. Is it on Wednesday or Thursday? We should figure that out.